hybridize to these fragments and see where it sticks. That hybridization process, I keep using that word, there's sort of three synonymous terms here. Base pairing, if you have two single strands that match each other, they're going to base pair. When they come together like that, we sometimes call that annealing. In metallurgy, annealing is when you melt two metals and allow them to fuse together. Okay, so this is analogous. We also call it hybridizing or hybridization. So those are kind of analogous terms. If you heat DNA to allow it to denature, to the two strands to come apart, and then you cool it gradually, what will happen is that the denatured, I don't know why they put it right to left instead of left to right on this picture. But anyway, you got two single strands. Actually, what they're showing is the opposite here. You're starting cold and you're warming it. You can go either way, right? So here's the double-stranded DNA. As you warm it, it begins to come apart more and more and more until they're completely split. This produces a sigmoid curve like this. In the middle of the log phase, right here, we call that the melting temperature of the DNA. Okay? So this is a kind of standard way to describe how much you have to heat a piece of DNA to split it, or how much you have to cool it to let it come back together. That becomes important in PCR, where we have what we call the annealing step. The temperature at which this TM, or melting temperature, depends, as I mentioned before, on how much of it is GC and how much of it is AT. Let's say that the TM of this molecule is right here at 83 degrees or so. If I give it more GC than it really has, if I increase the GC